Let's take a little deeper look at these networks and what some of the key components in the state of the art today. So here we show just a simple 2-node network. We have a QPU 1 on the left and QPU 2 on the right. Let's say you want to entangle and operate a gate, let's say a C0 gate, between qubit M on QPU 1 and qubit N on QPU 2. And so to do that, you'll need to be able to couple these to the outside world and have networking between them, connect them. You could do this with a superconducting wire, but that has a lot of challenges with scalability and density, and it's not likely to be able to reach those large sizes that we need. So then once you're able to connect these, you'll need to have a coupler to get to the outside world and a transducer, if necessary, to convert the frequency. So most of the quantum networks will operate at telco wavelengths, because these have the lowest loss and have the most common components that are developed in the field. And so you'll need to then convert your frequency in the quantum state that you have into another frequency, send down the optical fiber, do the reverse transduction if necessary to change the frequency, and couple into your other qubit on the other QPU. And so this process takes a while to explain, but it's going to be a very rapid process to support these applications. A little bit about the transduction there, we'll talk about today. It's possible to preserve that. One of the questions we have, it's possible to preserve that quantum state as you're changing frequencies, as long as you preserve that through the process and through likely a nonlinear process. The challenge there is the efficiency. So if the efficiency is not sufficiently high, you're not going to be able to have an effective gate. So if you're doing a C0 gate between qubit M and qubit N, if your fidelity of that transduction is 50%, you have to do a couple hops of that transduction. You're going to be around 10% fidelity for the gate, and that's not useful. In my experience, really can't use a gate that's much less than 90% fidelity. And of course, you want well over 99% fidelity too. And then there's a controller that's managing this, right? And so at Reliro, we work on all these components around the optical fiber and networking quantum devices and a controller to orchestrate these activities. So let's go a little bit deeper into the different components of the quantum network and why we are able to then believe we can work on this today. So there's a real strong call to action you saw about where we are in the scalability of quantum computers, some of the challenges and how to cross that divide into a fault-tolerant quantum computer. We've seen that the quantum chips are maturing and scaling. So I'll have a little bit of talk about how we're scaling up those numbers of qubits. We don't require the quantum repeaters to make this functionality work for a cluster network. There's varying levels of optical transduction required. We'll walk through some of the different types of that and the challenges. And fortunately, some of the QPU architectures today are photonically integrated. So superconductors will have more of a challenge with the transduction, but the optically interconnected ones will be a bit easier. And then finally, a really key point is why should we work on this now, networking these QPUs together? It's because understanding this entanglement-based networking performance limitations really helps us determine the requirements for a fault-tolerant quantum computer, because it's likely going to be a cluster and a network of multiple QPUs. And so understanding limitations of, what size of die should I use? How many multi-chips can I put? How far apart can the cryostats be? What's my conversion efficiency? What's the crosstalk level? Will then help design the better core of the QPU that then can be networked together into a cluster.